We're now going to look at a much more involved, thorough question that requires a lot of work. So let's break this down one at a time. Again, this is the function f of t, which zigzags like this, and we're defining a of x as being the area function, which covers the area between the graph of f of t and the t-axis from 0 to x. As we've said before, the area increases for a while, stays the same, and then the area starts to decrease since the graph is below the t-axis. Decreases for a while and then increases again. What this question is asking, for example, our part C, is find a formula for a of x. Find a formula for the area under the graph of f of t from a to x, which is a of x. We want a formula for that. But before we can do that, note that we pretty much are going to need a formula for f of t. And right now, we don't have a formula, we just have a graph that zigzags. So how would we go about finding a formula for f of t? Well, the way to think about it is the fact that this graph is cut into lots of different sections. And I'm going to try to color code this the best way I can. We'll say this is the first section. We're going to say that this is the next piece, right? And it's because it's zigzags. They're made up of different functions. It's a piecewise function. Then we have that piece, and basically it's going to zigzag and have piece here, piece here, piece here, and a piece there. So let's talk about the first piece, this little neon green. This is a horizontal line at t equals 1, right? So actually, this piece has an equation of f of t is equal to 1. Okay? This next piece, which I have in beige, has a different formula. Okay, if it were to extend up, you can see that it would cross at y equals 3 or f of t equals 3. We can use some math and conclude that the next part of this piece, okay, from 2 to 3, would be f of t equals 3 minus t. That's because it intercepts at 3 and it has a slope of -1. Basically, we're going to go through and we're going to determine a formula for all of these lines. Sometimes what you have to do is you have to extend the line to see where it crosses the t-axis. Okay, another thing you can do is just pick 2 points on the line and find a formula that way. But there's a lot of different ways to find formulas for these lines, and I'm not going to go through every single one step by step because this is algebra 1. But if you have a question about finding the formula for one of these, let me know. However, I've worked it all out already. So let's read this together. So remember that a of x is just the area from a to x of f of t. Ultimately, this question is asking for a function for a of x. So no matter what x value you or someone else picks, the function will return the area of the function of the graph of f of t. So what we're really saying is, we want to be able to pick any t value, and we want to determine what the area under this function, or area between the function of f of t and t is, the t-axis, for any particular t value. So for example, let's say we picked 4.5. We want to know the exact net area between f of t and t from 0 to 5.5 or 5.7 or whatever. We want a function for a of x to where when we plug the x value in, say 5.5, it will give us this area back. To do that, we've got to figure out formulas for these little lines first, and then recall that the definite integral, for example, from 0 to 2 here, would just be integrating this, or taking the antiderivative, which is x. So for example, antiderivative of this is x. If we plug in 2, we get 2 back, which confirms the fact this is a 2 by 1, right? But we can see that as the pieces change, it's going to change our answer. And that's where it gets more involved. Step 1, when determining an area formula, is to determine a piecewise function for the f of t function, or the original graph. Okay? We have to look at this function in chunks. A bit of inspection reveals it to be f of t equals 1 from 0 to 2. Let's begin this piecewise function. So, from 0 to 2, the function is f of t equals 1. What about the next piece? Okay? Well, I said there's different ways to do it. You can pick 2 points on the line, whatever. And again, we're talking about this piece right here. I've already determined it to be 3 minus t, but this is what happens if you pick 2 points. You find the slope given the 2 points, and then you figure out an equation for the line. Okay, you get the same thing, which is 3 minus t. I used x there. I shouldn't have. That should be a t right there, but it doesn't matter. This is the same as 3 minus t. Okay, similarly, the methods will produce the following pieces. And again, I wish I had more time to show them, but we understand that if you pick 2 points on a line, you can determine the formula for any line by finding the slope first, and then plugging in one of the points to find out b, and then you have an equation for the line. Okay, so similar points will produce, and this time I got the t right, it's t not x, will produce the following pieces. Okay, so I do want to break this down a little bit. So our next piece that we showed, which was this little blue piece, is obviously just t equals 0. We got the green, the pink, and the blue, and then all these other pieces. I'll at least color code the first 3. So here's our first piece. Okay, next piece is beige, actually not pink, and then the third piece is blue. So it's hard to bounce back and forth between these. Here's our next piece. Then our third piece is blue, and if we keep on going, these are the formulas for our other pieces. And that's it. So we have a piecewise function which gives us f of t for these different intervals, because for every interval the line changes. It's jagged, right? So there we go. Yeah, so now your mind is officially blown. Now that we've got the equation for this piecewise function, we're going to write the area function as the sum of the definite intervals. We have actually done a lesson where we found the definite interval of a piecewise function and where we've figured out the antiderivative of a piecewise function, meaning a formula. So for one thing, the formula for a of x has to be piecewise as well. The first piece is always the easiest. It's just the definite interval from 0 to x of f of t. So to determine the formula for that, just take the integral from 0 to x of 1, that first piece that kind of goes like this. And we get what? We get x back, right? And because when we plug in x into our integral, we just get x back, and then we plug in 0, we get 0 back. So the formula is x from 0 to 2 for a of x. What this means is that at the area of the graph of f of t from 0 to x up to including 2 is given by a of x equals x from 0 to 2. So let's go back to the graph and look at that again before we move on to the next piece. So from 0 to 2, we have f of t equals 1. The integral of that is x, right? Well, if we plug x into that, we still just get x back. And when we plug in 0, which is the starting point, we get 0. So the formula for this from 0 to 2 of the area would be just x. For example, if you plug in 1 for x, you get 1 back, which is the area into this first cube. If you plug in 2 back to x, you get 2 back, which makes sense because it's the 2 by 1. But now, the second piece changes that, right? So we have to use this formula to determine the area function from 0 to 3. Now here is the concept that's going to help this click for you. Can everybody see that once we get past 2, okay, this first area is not going to change. Once we get past that piece, it's always going to be 2, right? It's not going to be dynamic past 2 in terms of this first piece. It's a set 2 blocks, okay? What will change is from 2 to 3, it will change depending on this line. So fortunately, it's kind of easy in the fact that the first piece, once we get past 2, is now just going to be 2 plus whatever this definite interval is. So it changes from piece to piece, but once you get to the next piece, the other pieces are constant. You've already passed that area. You've already scanned past them, basically. So that will definitely help you understand this lesson a lot better if you understand that. Okay, so our first piece, as long as we're trying to find the area from 0 to 2, we just use x. But once we get past 2, things change. The next piece, you have to take into account not only the area from 2 to 3, but what came before it. And as I said before, that area is constant. It's 2. Okay? So we're finding the definite integral from 0 to 2 of that first straight line 1, which is just going to be 2, plus anything from 2 to x, or 2 to 3, is going to change depending on that formula for that line, which is negative 2 plus negative t plus 3. So what we get, again, is for our first piece, it's still just x from 0 to 2. Okay, but for our next piece, it's 2, that 2 by 2 block, or 2 by 1 block, plus 2 to x, and that goes from 2 to 3. And if we integrate that, we have to use the reverse power rule, -1/2 t squared plus 3t. That's from 2 to x, and that covers from 2 to 3 for x values. And once we simplify this, we have to plug in our upper and lower limit. So we have to plug in x for t for the upper limit. We have to plug in 2 for the lower limit, which is what I'm doing right here. So here's x being plugged in. Here's 2 being plugged in. And when we simplify that, we get, I'm just going to pull the 2 and move it over here, and then move the exponents in descending order. For the second piece, we get -1/2 x squared plus 3x minus 2. We can plug in any x value between 2 and 3 into this formula, and will give us the area back from all the way from 0 to 3, because we took into account that first area of 2. So in general, the area formula will look like this now. All the pieces will be depending on the previous pieces. Now, before we move on with all of that, I want to go over that second piece so you don't get too confused. So what that formula just gave us is if we plug in any x value between 2 and 3 into that formula we just got, it will give us the area of in between f of t and the t-axis from 0 to any value between 2 and 3. So for example, if we put 2.3, it'd be really hard to figure that out geometrically. If we had a formula, we could easily just plug in 2.3 to figure out what the area under the curve is from 0 to 2.3. And that's what this second piece gave us. Okay, again, I know this is a lot to digest, a whole lot to digest, and it can be very complicated, but that's why I'm going over it with you piece by piece. So that's what this is. So for example, if I plugged in 2.3 in for x, it would give me the area under the curve between the f of t and the t-axis from 0 to 2.3. That's why we want this formula. So in general, though, you just have to keep adding all of these previous area formulas up. So for example, if I'm figuring out the third piece, it would be right here. Now again, that area between 2 and 3 is set after you pass 3. Okay, in fact, it's just half of a block, so we know it's going to be 1/2. Again, I can go back and show you the graph again. That's going to help us understand this more. So from 2 to 3, this area is always going to be 1/2. This is always going to be 2. So for my third piece, I know I'm going to start out with 2.5 plus whatever that area is, which in this case is going to be 0. So the area from 3 to 4 is just going to be 2.5 plus 0, which is always going to be 2.5. After 4 is when it becomes dynamic again based on this piece. It's still going to be 2.5 plus whatever this area is, which will change depending on what point on this line we are. It's going to start to decrease, right? So you're always taking the previous areas and adding them to that particular piece that you're talking about as far as the function goes. Okay, so the third piece, okay, is going to be going from 3 to x. And again, that third piece is right on the t-axis, and it's just a straight line. It's just going to be 0. Okay, the fourth piece, we determine that the formula for that line to be -2t plus 8 will go from 4 to x, and in this case that line segment goes from 4 to 5. And again, we'll add all the areas before that. We'll take all the areas before that into account. In this case, like I said, if you just were to simplify all this, it would just be 2.5 plus this area formula. Okay, so I'm going to go ahead and move on and show you what the rest of the pieces look like. If we were going from 5 to 7, we have a different formula, which is t minus 7. And if we are going from 7 to 8, we have a different formula. It changes to -t plus 7. And then finally, we go from 8 to 12. That formula is 1/2 t minus 5. Just so you're not confused, I want to show what that looks like on the graph. This piece right here, from 8 to 12, its formula is 1/2 t minus 5. And that's this piece right here, 1/2 t minus 5. Okay, so that's where all of that came from. And if we evaluate all this and come up with different functions for different pieces, we can plug in any particular t value for that particular piece, or x value, for any number, any decimal number, and it will give us the area in between f of t and the t-axis for that number. Okay, so basically, we've already determined formulas for the first two, even the first three. We need to determine these formulas for the rest by evaluating all of these integrals. Okay, so step 3 is to determine the definite integrals. Again, you can go back and do the work yourself. That would take too long for this video. But for example, this piece right here, if you would just integrate that, take the antiderivative, plug in x, and then plug in 7, simplify. All these before it are constant numbers, so that's easy. And that will give you a formula from 7 to 8. So you put all that together, and I'm going to have to go this in chunks. This is the first piece, second piece, third piece, fourth piece, fifth piece, sixth piece, and that last piece, which we made light blue, that's the seventh piece. So for example, if I plugged in, let's say, 9 into this formula, that would give me the area between the curve of f of t and the t-axis from 0 to 9 into this formula, 1/4 x squared minus 5x plus 23. So if I plugged in 9 into that formula, it would give me this net area from 0 to 9. Okay. Now, that formula will give us that number, and it looks like it might be negative. I'm not sure yet. But another way to do this without having to determine the formula, the easiest way would be just to find the area of this rectangle, the area of this triangle, the area of this triangle, and if we were going to 9, we'd have to use a triangle, and it looks like a trapezoid. Okay, but sometimes, for example, if it was a decimal, you would want to use the formula, right? Because you don't know what the particular y value would be there. You had a formula for it. So that's why we need an area formula sometimes. But geometry works as well, like I said, when it's whole numbers. Okay, so this is going to be our answer, actually. Okay, this piecewise function will give us a of x for any particular x value, depending on which piece we're talking about. Okay, notice the third piece remains on the t-axis. The area remains 2.5 regardless of the increase in time. So I'm talking about this piece. From 3 to 4, the graph is right on the t-axis. So the area won't change. It will just be the area that was before it, which was 2.5. Okay, and that's that piece from 3 to 4. Okay, don't forget what this formula gives you. Pick an x value, any x value, plug it into this formula, this piecewise formula, and it will give you the area under the curve of f of t from 0 to x. Okay, that's it for this video. I know there was a lot in it. If you have any questions about it, let me know. I know this can be very confusing, and this is a very hard lesson to understand, so please let me know if you have any questions.